The intricate world of acoustic levitation would be explored, revealing how sound waves could be precisely manipulated to defy gravity. The cutting-edge engineering behind this fascinating technology, with its potential to revolutionize material handling and manufacturing, would be illuminated. Imagine lifting objects without touching them, using nothing but sound. Sounds like science fiction, right? What if I told you this isn't just a dream, but a cutting-edge engineering reality happening right now? Prepare to have your mind blown as we dive into the incredible world of acoustic levitation and discover how sound waves are defying gravity, revolutionizing everything from manufacturing to medicine. Tired of fumbling with delicate materials or dealing with contaminated surfaces in manufacturing? Get ready to witness a technological breakthrough that could change everything. We're about to unveil acoustic levitation, a revolutionary technique where sound waves are precisely engineered to manipulate objects with unprecedented control. Discover how this innovation promises to transform material handling and manufacturing, offering a cleaner, more efficient future. What if the very air around us could be harnessed to move objects with pinpoint precision? Forget magnets or robotic arms, the secret lies in something you hear every day. Join us on an incredible journey as we unravel the mysteries of acoustic levitation, revealing the ingenious engineering that allows us to suspend and manipulate matter using invisible forces. This isn't just a parlor trick, it's the future of material handling. Engineering sound for material manipulation involves using sound waves, particularly ultrasonic frequencies, to exert forces on materials, enabling precise control and movement of particles, even at the microscopic level. This technique, known as acoustic manipulation, has applications in various fields like biomedical research, materials science, and industrial manufacturing. Ultrasonic waves can be focused to create acoustic traps that can capture, move, and manipulate individual particles, cells, or even larger biological samples. This technique uses the force exerted by sound waves to separate and sort particles based on their size, density, and other physical properties. The speed of sound varies depending on the material's density and elasticity, which can be leveraged to control how sound waves interact with different materials. Gravity does not directly affect sound waves in the same way it affects objects with mass. However, gravity can indirectly influence sound by affecting the medium through which sound travels, such as the atmosphere. For example, gravity compresses the atmosphere, leading to variations in air density and pressure, which in turn affects the speed of sound. Additionally, sound waves can be used to counteract gravity, as seen in acoustic levitation. Sound is a vibration that travels through a medium, like air, as a wave. It doesn't have mass in the traditional sense. Gravity pulls on the air, creating a denser atmosphere near the Earth's surface and a less dense atmosphere at higher altitudes. This difference in density affects how sound waves travel through the air. Acoustic levitation is a technique that suspends objects in midair using focused sound waves, specifically acoustic radiation pressure. It's a way to counteract gravity by creating a standing wave where the pressure is high at certain points, trapping the object against the force of gravity. This principle is similar to acoustic tweezers, but levitation focuses on overcoming gravity while tweezers are typically used for smaller objects in liquid media. Acoustic levitation uses sound waves, often at ultrasonic frequencies, to generate a standing wave pattern in the air. These waves have regions of high pressure, antinodes, and low pressure, nodes. Objects can be suspended at the antinodes where the pressure pushes them upwards against gravity. The acoustic radiation pressure from the sound waves exerts a force on the object, counteracting the force of gravity. Standing waves can create pressure traps by causing pressure variations within a medium. These variations can lead to regions of high pressure, antinodes, and low pressure, nodes, effectively trapping particles or objects within these pressure zones. This phenomenon is utilized in various applications like acoustic levitation and particle manipulation. Ultrasonic transducers are fundamental to acoustic levitation because they generate high-frequency sound waves that, when reflected, create standing waves. These standing waves have areas of high and low pressure, and objects can be suspended at the pressure nodes, effectively levitating them against gravity. Engineers manipulate frequency and phase to control and shape waveforms in various applications, including audio systems, radio communication, and signal processing. Frequency manipulation involves changing the rate at which a signal oscillates, while phase manipulation alters the alignment of waveforms in time. Many materials can be levitated using magnetic fields, including diamagnetic materials like water, biological organisms, and certain plastics. These materials are repelled by magnetic fields, and when placed in a strong enough magnetic field gradient, the repulsive force can counteract gravity, allowing them to levitate. Strongly diamagnetic materials like pyrolytic graphite and bismuth can also be levitated. These materials are weakly repelled by magnets. When placed in a strong magnetic field gradient, the repulsive force can be used to levitate them. Examples: water, ethanol, acetone, bismuth, antimony, graphite, wood, plastic. Acoustic levitation, the ability to suspend objects using sound waves, has several real-world applications, primarily in fields requiring contact-free material handling and manipulation. Industries like pharmaceuticals, microchip manufacturing, and scientific research are finding uses for this technology. Acoustic levitation allows for the handling and processing of delicate materials without physical contact, preventing contamination and damage. This is particularly useful in the manufacturing of microchips and other small, sensitive components. It also allows for the study of high-purity materials or chemical reactions that would be affected by a container. Acoustic levitation is used to study the behavior of liquids, including chemical and biochemical reactions, without the interference of container walls. The technique can be used to apply controlled forces on molecules, which is useful for studying their mechanical properties and behavior. Levitation in 3D printing, particularly using acoustic or magnetic forces, enables support-free fabrication and opens possibilities for advanced manufacturing. This technology allows for the creation of complex, multi-material objects by manipulating materials in mid-air, potentially revolutionizing various industries. Acoustic levitation uses sound waves to suspend and manipulate materials. High-intensity ultrasonic waves create pressure nodes that can trap and hold objects, allowing for contactless 3D printing, a system that utilizes acoustic levitation for 3D printing and assembly, enabling the manipulation of elongated objects like sticks and beads. Magnetic levitation relies on magnetic forces to suspend and manipulate materials. Superconducting materials can be used to create strong repulsive forces, allowing for levitation and precise movement. Precise control over particle movement, high-throughput sorting capabilities, and the ability to integrate with other technologies. Acoustic levitation, while offering fascinating possibilities, requires careful consideration of safety, primarily due to the high-intensity sound waves involved. Key safety concerns include potential damage to hearing, the possibility of object instability and unintended movement, and the need to protect against stray radiation. Acoustic levitation, while promising, faces several challenges including limitations in scalability, stability, and energy efficiency. Additionally, the properties of the object being levitated, size, shape, and material, and the sensitivity to external factors like noise and vibrations can affect the levitation process. Furthermore, achieving precise control over levitated objects, especially at higher speeds, and preventing droplet atomization are ongoing areas of research. Acoustic levitation could be used to assemble complex structures at the microscale, such as microrobots or intricate medical devices, by precisely positioning and joining components without physical contact. It could enable containerless processing of materials that are highly reactive, corrosive, or require ultra-high purity. Imagine melting and solidifying materials in mid-air, creating novel alloys or pharmaceuticals with unprecedented purity. By suspending and precisely positioning cells, acoustic levitation could be used to 3D print complex biological structures, potentially leading to the creation of functional tissues and organs for transplantation. These are just a few examples of the potential applications of acoustic levitation. As the technology continues to advance, we can expect to see even more innovative and mind-bending uses emerge in the years to come.